Hello everyone, this video covers problems 1 to 5 from Think Through Geometry. If you haven't purchased the book yet, I've included the URL in the description of this YouTube video. Alright, so problem number 1. How many distinct points are minimally required to form a unique line? So first off, we draw a dot. There must be a dot A, call it A, and there must be a dot B. And we know from the postulate and we know from the properties and just definitions that we just need at least two different points to form a unique line. So the answer for the given problem must be 2. Number 2, how many distinct non-collinear points are minimally required to form a unique plane? So it should be non-collinear points, and if I just underline non-collinear points, it means that they're not staying on the same line. So if you just think about drawing a triangle, you can consider these piece of paper or the screen that you are actually looking at as a plane that is containing A, B, and C. So if I just graph a plane that is containing A, B, and C, you can see from the screen that this particular flat surface that does not end right here. It extends infinitely many directions, but that's going to be a unique plane. So we just need 3 different points, but they should be totally non-collinear. Number 3, given a tetrahedron, first of all, we just have to remember what tetrahedron is. If you think about tetrahedron, that must be a 4-faced figure. And 4-faced figure, you can call this as a pyramid. It must be a 6-edge polyhedron whose faces are equilateral triangles. So definitely this must be a isosceles, we can say regular tetrahedron. How many faces are there? We can count them directly. We can consider this face that actually looks towards us, and another one, and you can see the unseen one, and the bottom one. So you can consider this as 4 faces. Now, problem number 4, it says, in how many ways can one connect 2 different vertices of a regular heptagon? So if you think about a regular heptagon contains 7 points. So it should be 7 points. You draw the 7 points, 1, 2, 3, 4, 5, 6, and 7. You can label these. And first, as soon as you label such points, well, I think we can choose one of the points. So step number 1 would be choose one of the points. So we have 7 choices to choose the first point. And step number 2, there must be 6 choices to choose the second point. Now that indicates that we have 7 times 6, but the answer is not 42 though. The answer is going to be 21. The reason why it's going to be 21 is because if you connect 1 and 4 together, you can actually see that 1 and 4, the segment, must be considered the same way as 4, 1. So because we have that type of properties for the segments, we got to say we need to divide it out by 2 to get rid of the overcounts. So the answer becomes 21. So yes. Now number 5. A regular hexagon has n number of diagonals. Recall that a diagonal is an edge connecting 2 non-adjacent vertices of a given polygon. What is the value of n? Right, so we have a regular hexagon, and if you think about a regular hexagon, you can actually identify all shapes of diagonals by sketching it. And in fact, we have these type of diagonals, and of course, we also get the longer one, which is containing these pieces all together. So if you think about sketching everything, well, as you can see from this picture right now, we just have 15 number of cases. So we, first off, we would say 6 choose 2 would be 15. And for those people who forgot about how to do those 15, well, here's what's up. 6 times 5 divided out by 2 times 1. That must be 15, but we need to subtract some cases, right? We need to find out the diagonals. How do I find out the diagonals? Diagonals are going to be found by subtracting the number of edges. So if you think about it, let's just try to count this directly. 1, 2, and 3. 4, 5, and 6. And if I just change the color into the black, 7 8, and 9. And that indicates that we just have to get rid of 6 regular edges. So that means we have 9 diagonals. Right, so the answer for